Hello. In this lesson, I would like to, first of all, reintroduce the row theorem and the mean value theorem. And also, we like to talk about some other uses, other applications of these two theorems, okay? And as we understand from the beginning, when we first introduced the Rolle's theorem, it seemed that the Rolle's theorem has applications. We've done some exercises in the previous recordings and in your homework. And the other application of Rolle's theorem is to prove mean value theorem. If you recall and have watched the proof of mean value theorem. So the second application of Rolle's theorem, besides those questions we did in class, is to prove mean value theorem. And then what? What do we use mean value theorem for besides all of these we have covered? Well, in this lesson, we like to introduce two more useful theorems. These two more useful theorems actually has a lot to do with materials we are going to cover next after this. Okay, the first one. Okay, so let me write down the statement. The theorem says if the derivative of a function, so we have a function, its derivative is equal to 0 for all the numbers x, okay, in a specific interval. Okay, in a specific interval, a comma b. So we have an interval which is open interval, and for any x in this interval, derivative of the function is 0. Okay, and then what can we tell about this function? Then we have this conclusion. Okay, then the function is a constant. Okay, then we can say the function is a constant. Is a constant in the interval AB. Okay, so let's see how we can prove this theorem, and then we're going to talk about and the implications of this result. Okay, so proof. So first of all, what does it mean a function is a constant? Okay, a function is a constant means for any input, right? For any input, the output is always the same number. Okay, so let me put in a note. A constant means for any input, and in our case that the input is from this interval, right? Any input, and this input is supplied to the function, it produces output. And the output, no matter what the input, is always a constant. That's what we mean, that it is a constant function. It's a constant function. That's the meaning of a constant function. So for any, and this is true for any x, right, in the interval AB. All right, so that's the meaning for a function to be a constant, to be a constant in an interval. So we are going to prove that. We're going to prove that. In order to prove this, we're going to choose values arbitrarily from the interval. Okay, we're going to choose values from the given interval AB. So we're going to say let x sub 1 less than x sub 2, okay? And they are in this interval. X1 is larger than A and X2 is smaller than B. Okay? So X1, X2 is any two numbers in the interval, arbitrarily chosen. Okay? Now we're going to have the following statement. Since f is differentiable, we know that if a function is differentiable, it's continuous, right? Since f is differentiable in the interval AB, then it must be differentiable. Okay, then it must be differentiable. It must be differentiable in the interval that's inside of it. Okay, it must be differentiable in x sub 1 and x sub 2, closed interval. Okay, and if it is differentiable, it's continuous. So it must be differentiable in this. We just try to match the conditions in the mean value theorem, right? It's differentiable in this interval and continuous on the closed interval. Okay, because the two numbers we have chosen. Then we can now apply mean value theorem. Okay, apply mean value theorem. Okay, to F. And since both conditions are satisfied, we can claim there exists, and the mean value theorem is applied on this subinterval inside AB. Okay, so there exists. Okay, so we're gonna just copy the sentence, right? We're gonna copy the sentence, right? Except it's on that's the interval x1 to x2. There exists a C, okay, and C is in x1, comma x2, such that the conclusion of the theorem applies, of mean value theorem applies, which is the derivative of the function evaluated at C is equal to the endpoints, right? The endpoints. A, B minus A, RB is x sub 2, RA is x sub 1. Okay, let me make it 300%. Let me make it larger. Okay. And on the top is f of x2 subtracting f of x sub 1. All right. Then because the derivative is equal to 0, right? Since the derivative equals to 0, then the derivative at C is also equal to 0, right? So we're going to quote, whoops, let me change a line. Since, right? We're going to quote this condition for, this is true for all the values in the interval, and x sub 1 comma x sub 2 is a subinterval. Thus, the derivative of a function at c, which is in the middle, is inside of it, is also equals to 0. And that is, this is going to lead us to that the whole thing is equal to this piece is 0. If this whole piece is equal to 0, denominator x2 minus x1 is not 0 because we know x2 is larger than x1. So this will lead us to that f of x2 minus f of sub x1 must be 0. And what does that mean? That means f of x2 and f of x1, they are equal. And remember that x1 and x2 are chosen arbitrarily. They're chosen arbitrarily. Okay? Since they are chosen arbitrarily and arbitrarily chosen x1, x2 from A, B, they have the same function value, and therefore we can say the function f must be a constant. Must be a constant on this specific interval AB. So that's the end of the proof. That's the end of the proof. Okay. We know, right, from our previous studies, right, that if two functions are the same, when their derivatives are the same, right? But what if the derivatives are the same? What can we say about the function? And our next theorem, as a corollary of this theorem, okay, corollary of this, the theorem we just did, it says if f of x and g of x have the same derivative, so f of x, the derivative of f is equal to the derivative of g for the same interval, okay, for all the x inside the interval AB, okay? I do the copy and paste because I want you to see these conditions are comparable, okay? And then what? Then f of x, okay? The condition is the derivative are the same for all the x in a particular interval. Then f of x minus g of x is a constant. And as a result, okay, that means that if f of x equals to, if f of x minus g of x is a constant, then f would be equals to g of x plus the constant. So this is another way to say if two functions have the same derivative, then these two functions are only different by a constant. So we're going to prove this. Okay, we're going to prove that. All right, so proof. When we prove this theorem, we are going to introduce a function, we call it h, lowercase h. Okay, h of x equals to f of x minus g of x. Okay, we'll say let h of x equals to f of x minus g of x. And because the derivative, so we're going to take a derivative. right? So then the derivative of h of x will be the difference of a derivative. So we take a derivative here, this will be derivative, and this will be derivative. What will that be equal to? That will be equal to 0 for all the x's on the interval, right? Because the two derivatives have the same derivative. And then we just apply the theorem, right? The theorem above, if the derivative equals to 0, right? On the interval, then the function is a constant, okay? Apply the theorem, we got the derivative, h of x is a constant. If h of x is a constant, and that means f of x minus g of x is a constant, i.e., okay, that is, or the theorem is proved. We have just done that, right? If we can prove the difference is a constant, then the two functions are different by a constant. So this is the end of the second important theorem, even though it's called a corollary because it is in relationship to the theorem we just proved. So this is to summarize, and what's the use of it? We are definitively going to use these results in the future and in the near future. So now we know that if two functions, right? So we're going to have the following discussion. If two functions are the same, right? If f of x is equal to g of x, then their derivatives are the same. That's easy. We just take a derivative on both sides. We've used that many times over, right? In implicit differentiation and many other cases. And of course, you can say we do this for a specific interval. Sometimes it's on entire domain. Then you say, well, if two functions are the same, why do you take derivatives separately? Well, usually those are in equation settings. However, if the two derivatives are equal, the two functions have the same derivative, and we say the two functions are the same, the answer is no. One function is different from the other by a constant for all the x in an open interval. Okay? And what is the use? We're going to be using this in the future course, in the future sections on antiderivative, and the sections that that's gonna come next. Okay. So thank you for watching, and this is a very important content. And I hope you guys get to study this and understand it. I think maybe I can give you an example about how this works. Okay, so let's give some examples. For example, okay, suppose I have one function f equals to e to the power x, right? Another function g, it will be equals to e to the power x plus a constant, right? And obviously these two functions are not the same, but their derivatives are definitively equal because the derivative of constant is 0. So we have plenty of such examples. Okay, so we're going to see more when we get to the following contents. All right, thank you for watching.